Alright, this video is about potential difference. It's one of the absolutely key underlying ideas that we need to be able to explain DC circuits and how they operate, and it's also quite a complex and quite a difficult one to understand. We're going to start at the beginning with charged particles, because ultimately that's what DC circuits are all about. If I have a couple of charged particles and they are like charges, they repel each other. That is a fact. That is how we know they're charged. These two repel each other. So what happens if I bring them closer together? Well, for me to bring them closer together, I have to overcome that repulsive force and I have to move them. So supposing I go from these two at the top to these two at the bottom, which are a much closer distance. The size of that repulsive force actually increases, but I'm not too concerned about that at present. Just that there is a repulsive force. What's happened here then for me to bring these closer together is that I've had to do some work. Remember, in physics, the definition of work is force times distance moved in the direction of the force. So if I've done work, I have transferred energy. So you can imagine having two charged particles, a bit like two magnets that repel each other, and for you to push them together, you're having to put some energy in, you're having to do some work. Where has that energy gone? Because you have definitely transferred energy to these particles, and they started stationary, they've ended up stationary. So where has my energy gone? Well, it is stored as potential energy. You could think of it as there being a sort of spring between these two particles pushing them apart. If I squeeze that spring, I'm storing energy in it in the form of potential energy. I can get that energy back. If I release these particles, they fly apart and that energy turns into kinetic energy, for example. Interestingly, in this scenario, the closer together these two charged particles are, the more potential energy they have got by conservation of energy. Because the closer together they are, the more work has been done to bring them together. Think about this little thought experiment. Suppose I have a box in which I place some charged particles. They all have the same charge. If I leave these particles alone, they all repel each other, so they will spread out as far from each other as they can possibly get. And you could imagine finding these particles kind of one in each corner, for example, and maybe one in the middle. They have spread themselves as far apart as they can possibly be. If I were to put a lot of charged particles into the box, I'm not going to draw too many because it'll take a long time. You could imagine that they would spread themselves out evenly, because if they're not evenly spread, they would have net forces on them. So if I go back to this this idea that the size of this force depends on the distance, the only sort of position one of these particles can be in where it's in equilibrium is the same distance from its neighbours, so that the forces on it can balance. So I would expect the charged particles inside this box to all be relatively evenly spaced. They might be jiggling about some, but on average, evenly spaced. What happens if I add another particle to the box? Well, if I put another one in, the particles will reshuffle themselves to become evenly spaced again. But importantly, the distance between the particles on average will be less. And if the distance between the particles is less, there is greater potential energy. So remember from this example of just having two particles, the closer together they become, the higher the potential energy stored in them. So if I make all of the particles inside this box closer together, they have greater potential energy. So now think about what happens if I have two such boxes. I'm just going to try and grab this and copy it. get rid of my little arrows. Whoops. Might have to. Oh no, that hasn't gone well for me at all. I'll redraw some of my particles. I've got two boxes that contain evenly and equally spaced charged particles. So the average spacing between the particles in each box is exactly the same. Therefore, the potential energy of each particle in each box is exactly the same. What happens if I start taking particles out of here and putting them into here? Well, what will happen is, again, if I introduce new particles to this box, the particles will shuffle themselves about until they are closer together. And these ones will have higher potential energy. These ones, as I remove particles from the box, these will spread into those empty gaps, and the distance between these particles on average will increase, and therefore it will have lower potential energy. So by moving charged particles from one of these to the other, I've created a difference in the amount of potential energy for each particle in the box, for each and every particle in the box, not just the ones that I've moved. Every single particle in here now has a higher potential energy than every single particle in the second box here. So with that in mind, what goes on inside a normal DC circuit to produce that difference in potential energy, and why or how does that lead to this phrase, potential difference? I mean, already, if I'm talking about a difference in potential energy, you can probably feel that there's some sort of link there between that and potential difference specifically. I'll start with the word potential. When we talk about potential rather than potential energy, what we're talking about is potential energy per unit of charge. So remember I said here in these boxes, these ones have a higher potential energy. Each one of them has, but I haven't actually counted how many particles are in the box, and I don't know, therefore, the total amount of potential energy, and neither does that really matter. The important thing for me is how much potential energy there is, if you like, for each particle, or better still, since the charge of each particle is tiny, how much potential energy is there for each coulomb of charge, because that is a useful quantity. So when we talk about potential, we're talking about the potential energy per unit of charge, the potential energy of each coulomb at a particular location. So potential difference is, as the name suggests, simply a difference in the potential energy of each unit of charge between two places. I'll repeat that in a moment, and that hopefully this idea will start to kind of make sense as we apply it to an actual circuit. Let's think about what happens inside a circuit. If I build a simple circuit, I've got this type of setup. I've got a cell with a positive side and a negative side, and I've got a resistor. How does the cell make this positive side and negative side? Well, basically inside a cell, and this is a very simplified version of what happens inside a cell. Inside a cell I have two chemicals, and the chemical reaction between them. Remember that chemical reactions are mostly about rearranging electrons, either distributing electrons between atoms or moving electrons from one atom to another. The nature of the chemical reaction in this cell takes electrons from one end of the cell and moves them to the other. What that means is that I have a high concentration of electrons at one end and a low concentration at the other. So you can think of, going back to this idea of me moving charged particles from one of these to the other, it changes the amount of energy per charged particle in each of these locations. What that means inside my cell is that an electron at this end has a different amount of potential energy than an electron at this end. A coulomb of charge at this negative end has a different amount of energy than a coulomb of charge at this positive end. And that is what the potential difference is. It's that difference in potential energy per coulomb of charge based on where we're looking in the circuit. So I have got a potential difference between the ends of this cell. And that potential difference comes about from the difference in the sort of concentration of these charged particles. So that's what's happening inside the cell to create that potential difference, to give me a positive side to the cell and a negative side. What goes on in the circuit then, if I think about this simply in terms of forces, this is a reasonably straightforward way to think about this. If on one side of this cell I have a high concentration of electrons, if I'm an electron near that, I have a repulsion from that high concentration. If I've got a low concentration of electrons on this positive side and I'm an electron near that, I feel attracted to that region, because if there's a low concentration of electrons, remember that the cell also has positive ions, there will be a high concentration of positive ions. So in that way, this cell applies a force to those electrons to encourage them to move. That is where the phrase electromotive force comes from, or EMF. This resistor is trying its best to prevent electrons from flowing through it. So what we would find in this circuit, if we could check the concentration of electrons, is that around this whole side of the circuit there is a high concentration of electrons, meaning that all of this metal has a higher than normal concentration of electrons and is negatively charged total. And on this side of the circuit there is a shortage of electrons, a lower concentration than normal, meaning that all of the metal in these wires is slightly positively charged. And for that reason, if I looked either side of this resistor in the copper wires there, I would find that again I have got a potential difference entirely arising from this concentration of electrons, that difference in the concentration of electrons on one side of this resistor compared to the other. So remember again, that concentration of electrons, the closer they are together, the more energy each one of them has got. And we use that term potential to mean potential energy per unit of charge. So when we consider two locations in a circuit, we find that we can have a potential difference between two locations if there is a difference in the concentration of those charge carriers, those charged particles, the electrons that are free to move. Okay, let's briefly talk about units and then I'll wrap up. So units for potential difference are volts, capital V, and this is somewhat interesting. Obviously the letter we use to represent potential difference is also V. So V is measured in volts as well. Potential difference measured in volts, but also represented by the letter V. 1 volt represents 1 joule of potential energy per coulomb of charge. Oops. Technically, 1 joule should have a lowercase j. 1 joule per coulomb of charge. So when I see something like a battery, a cell, maybe it's a AAA or something like that, and it says on it 1.5 volts, that means if I was to isolate a coulomb of electrons at this end of the cell and a coulomb of electrons at this end of the cell, these ones have 1.5 joules more potential energy than these ones. And if I was to do the same thing with protons, a coulomb of charged particles at this end of the cell, positively charged particles, protons, have 1.5 joules more potential energy than at this end of the cell. That is what that 1.5 volts